Hello friends, in today's question, two uniform rods A and B of length 0.6 meter each and mass is 0.01 kg and 0.02 kg respectively are rigidly joined end to end. The combination is pivoted at the lighter end P as shown in the figure, such that it can freely rotate about the point P in the vertical plane. A small object of mass 0.05 kg moving horizontally hits the lower end of the combination and sticks to it. What would the velocity of the object so that the system could just be raised to the horizontal position? So we have two rods A and B, and this is the small object whose horizontal velocity needs to be found out, and such that this system of lighter as well as heavier rod just comes to the horizontal position. So in this case, first of all, let us find out what will be the moment of inertia of the system. Let us say moment of inertia of the system includes rod A, rod B, and the particle which sticks to rod B. First of all, let's find out for rod A, and the pivot point is P. Rod A and pivot point is our P. In this case, so if this is our rod A and pivot point P, we have its mass MA and the length, let us suppose, is given as L. Therefore, we can find out its moment of inertia about this point P. So therefore, we can write that moment of inertia about point P, let us suppose it is written as I for rod A about point P, will be equal to M 1 by 3. We have MA and we have its L square. So this is for rod A, and let us write for rod B. So for rod B, the pivot point is still P. Pivot point is P. Therefore, for rod B, rod B will be combination of rod A as well as rod B, or the pivot. So we have, this is our rod A, and to this rod B is welded like this. So we are given, this is rod A, mass A, rod B, let us suppose its mass is given as LB, and the length of rod A is L. Similarly, the length of rod B is given as same, so let us this be also L. So if this is the center of rod B, then this will be equal to L by 2, and total length will be equal to L plus L by 2, and this is pivot point P. So we want to find out the moment of inertia of rod B about the point P. Okay. In this case, first of all, let us find out what will the moment of inertia of rod be about its center, and then we are going to use theorem of parallel axis to find out its moment of inertia about point P. Okay. Let us say moment of inertia of rod B about its center So we have this as I for rod B about its center, and that will be given as 1 by 12 MB, and we have L square. Now using theorem of parallel axis, moment of inertia of rod B about point P, and we can write this as I of rod B about point P will be equal to moment of inertia of rod B about its center plus mass of the rod B, which is given as MB, multiply the distance between, perpendicular distance between the point and the center, L plus L by 2 and its square. So if we substitute the values, we get this as 1 by 12 MB L square plus MB multiplied by, we have L plus L by 2 and its whole square. Next is the moment of inertia, because this small object sticks to the rod at the lowest end, this point. So we are going to find out its moment of inertia about point P. Therefore, we can say moment of inertia due to small object about point P, about point P. So let us redraw the figure. So if we have rod A, and then we have rod B, and to this rod B, this is our object. So we have length L of rod A, length L of rod B, so total length will be equal to 2L. So this is mass of rod A, mass of rod B, and let us suppose M is the mass of object. So we can write, and once again this will be point P. Therefore, so moment of inertia of object about point P will be equal to its mass, that is given as M, and the total distance, that is 2L and its whole square. So therefore, the total moment of inertia of the entire system about point P total moment of inertia of the system about point P we can write, let us suppose that is given as IP, which will be equal to moment of inertia of rod A about point P plus moment of inertia of rod B about point P plus moment of inertia of the object about point P. So we already found out the respective formulas. We substitute, this becomes m upon L square by 3 plus we have 1 upon 12 mb L square plus mb L plus L by 2 whole square plus, and we have m 2L whole square. Now we substitute the values. This is equal to MA, that is the mass of rod A, is 0.01 and the length is given as 0.6. So with the 0.6 whole square divided by 3 plus 1 by 12. MB is given as 0.02. Length is given as same plus 0.02, and the length will be here 0.6 plus 0.6 upon 2 and its whole square, and finally plus mass of the object is 0.05 and the total length is 2 into 0.6 whole square. Yeah. So this solution will be coming equal to as 0.0012 plus 0.0006 plus 0.02 multiplied by 0.81 plus 0.05 multiplied by 1.44, which comes as 0.0012 plus 0.0006 plus 0.0162 plus and 0.072. So therefore our IP, moment of inertia of the system about point P, this will be coming as 0.09 kg meter square. Okay, so this is moment of inertia of the system. System is our rod A plus rod B plus object about point P. So this completes our first part, that we found out what will be its moment of inertia. Now we are going to use the conservation of angular momentum. Conservation of angular momentum. It means initial angular momentum should be equal to final angular momentum. So therefore we can write that our initial angular momentum, which means basically before collision, and under this condition only object is moving, the rod, which is a combination of A and B, is stationary. Okay. So in which only object is moving, okay, with velocity u. So only object is moving. So therefore we can say that our L initial is equal to mass into initial velocity into length, that is 2L. So we got the initial angular momentum. Now we are going to find the final angular momentum. Final angular momentum, which basically means after collision, and after collision means the whole system is moving. Whole system means rod A plus rod B plus object is rotating, and let's suppose it is rotating with angular speed omega. Is rotating with angular speed omega. Therefore we get L final will be equal to total moment of inertia about point P multiplied by the angular velocity I P into omega. So conservation, we have conservation of angular momentum. L initial is equal to L final. L initial is equal to L final. So initial was equal to mu multiplied by 2L, and final is upper IP multiplied by omega. So mass of the object is our 0.05, initial velocity is u, and twice multiplied by length, that is 0.6 meters, is equal to IP we found out is 0.09 multiplied by omega. So we can write that our omega will be equal to 0.06 divided by 0.09 times u. So from here omega is equal to 0.67 times u. So we found out relationship between the angular velocity as well as your linear velocity. Linear velocity is of mass and angular velocity is for entire system. Okay. Let us call this equation number 1. Now we are going to use the conservation of energy. Conservation of energy. So it's asked that just after collision the system should be raised up to the horizontal position. Okay. So from here we can say that after collision for the system, and system is rod A plus rod B as well as object, for the system to just reach horizontal position, all kinetic energy is converted into potential energy at the horizontal point. All kinetic energy is converted into potential energy at horizontal position. So therefore that is kinetic energy immediately after collision. We can say kinetic energy immediately after collision. Let us suppose this as K initial will be equal to half IP into omega square, and it will be converted into potential energy in the horizontal position. So initially the rod is, or we can say system is in this position. So we have a rod A, and to this rod B is connected, and to this we have an object, that is, this is the object. So we have MA, we have MB, and we have an object which mass is M. And when it is being stuck with initial velocity of U, this system, and this is point P, this system is going to rotate in this direction. So we are going to have rod A, and we are going to have rod B, and we are going to have an object in this position. Okay. So we say let this MB, this is the center of mass for rod B, and this is the center of mass for rod A. So this object M, it is going to traverse this path and will be reaching this point. So the height through which this object comes to the horizontal position, which will be nothing but 2L. This is for object M. And for the rod B, this is center of mass, and this center of mass will be traveling something like this and this point. Okay. So we have this length as L, and this length will be per L by 2. So the total length through which the B rod travel, or it is center mass travel, is L plus L by 2. Okay. And finally, this is rod A, and its center of mass will be traveling like this to this position, and this height will be given as L by 2. Okay. So we have this as center of mass rod A, center of mass rod A, and for this we have center of mass rod B, and this is our object. So we found out that the object comes to the horizontal position through a distance 2L, and the rod B having a center of mass at this position, it comes to the horizontal position as L plus L by 2. Let me write this as B, and this is for object, and this is for rod A. So we found out the distance traveled, vertical distance traveled rather, by rod A, rod B, as well as rod C. So this will be center of mass for rod B, and this will be center of mass for rod A, and this will be object M. So therefore we can say the potential energy when the system is horizontal, total potential energy rather. So we can say potential energy when the system is horizontal. So let us write this as P final P final will be equal to potential energy of rod A plus potential energy of rod B plus potential energy of object. And we know their respective heights through which they have individually traveled. So we can write this will be equal to mass of rod A, G, and height traveled by rod A, its center of mass is L by 2, plus we have MB, G, and the distance traveled, vertical height rather, is L plus L by 2, plus object mass is M, is G, and the total distance traveled is 2L, vertical distance. Now we substitute the values. So MA is our 0.01, 10, and the length is our 0.6 divided by 2, plus B is given as 0.02 multiplied by 10, and this is our 0.6 plus 0.6 divided by 2, plus mass is given as 0.05 multiplied by 10 and multiplied by 2 into 0.6. So therefore we get the final final potential energy will be coming as 0.81 joules. Conservation of energy. Kinetic energy initial will be equal to potential energy final. Conservation of energy. We have kinetic energy initial will be equal to potential energy final, and half IP multiplied by omega square is equal to 0.81. Substituting value of IP, and we get this as half IP we already found out is our 0.09 multiplied by omega square is equal to 0.81. Therefore we can write that our omega will be equal to omega square is 0.81 and divided by 0.045, which will be coming as 18. So for going omega is equal to square root of 18 approximately, which will be coming as 4.2 radian per second. So we found out the angular velocity, and we already know the relationship between the angular velocity as well as the velocity u, that's the velocity of the object, from equation 1. So we can say from equation 1 we get (0.67 u is equal to 4.2. Also from here we can say u is equal to 4.2 divided by 0.67, and so we get u is equal to approximately 6.3 meter per second. So this is the velocity of the object. This is the velocity of the object, so that the system is just raised to horizontal position. Okay, so this completes the question. Thank you.